chemistry and all the things. So today our topic is that calculus, right? So under the calculus topic we have to cover lots of things like that, as per your syllabus. So I have seen that is limit, continuity, differentiations, that applications of a limit, continuity, and all the things, application of a calculus. We'll go through that one. So starting with the topic that is limit, how do you understand what is the limit, and how it limit is, that is what is limit and what is continuity. So you have learned these things, basic things, in the lower classes like your graduation, and also in the 10+2. So that system. So the thing is that today we'll go through this limit and continue. Let's understand by that video lecture. So what is, how we'll see that limit, and what is the continuity and all the things. So let's start with that one.
वन पॉइंट थ्री देखेंगे, जिसमें हम लिमिट्स एंड कंटिन्यूटी के कॉन्सेप्ट को सीखेंगे। तो अगेन जो ये लिमिट्स का कॉन्सेप्ट है, ऑल्दो तो कंसेप्चुअली बहुत सिंपल है, लेकिन ये कई सारे बहुत कॉम्प्लिकेटेड कैलकुलेशंस को आसान बनाने में मदद करता है, और ये इस कोर्स में भी, जैसा कि हम आगे देखेंगे, बहुत कारगर साबित होगा। तो लिमिट्स क्या होती है? सपोज हम एक फंक्शन लें, सपोज लेट्स से साइन ऑफ एक्स, जो कि शायद हमारा फेवरेट फंक्शन बन चुका है अब। साइन ऑफ एक्स, तो जैसा कि हम जानते हैं ये 0 पे 0 होता है, फिर बढ़ता है 1 तक जाता है, फिर 0 पे आता है, फिर -1 पे जाता है, फिर 0 पे आके 1 तक जाके, ऐसा ये पीरियोडिकली चेंज होता रहता है। उसी तरीके से नेगेटिव साइड में भी वैसा ही सेम होता है, कमता है, बढ़ता है, 0 को क्रॉस करता है, और ये -इन्फिनिटी तक हम जब जाते हैं रियल लाइन में, तो ये ऐसे ही ऑसिलेट करता रहता है। और ये जो पॉइंट्स हैं ये हैं 0, पाई, 2 पाई एंड सो ऑन, और यहाँ पे -पाई, -2 पाई एंड सो ऑन। तो अभी मैं अगर आपसे पूछूं कि ये जो फंक्शन है साइन ऑफ एक्स, उसकी 0 पे क्या वैल्यू है, तो आप मुझे बहुत आसानी से कह सकते हैं कि साइन ऑफ एक्स की वैल्यू एट x इक्वल टू 0 इज 0। सो यानी कि एट x इक्वल टू 0 साइन ऑफ x इज इक्वल टू 0। अब आपसे ये पूछने के बजाय मैं अगर आपसे ये पूछूं कि आप 0 को अगर लेफ्ट साइड से अगर अप्रोच करते हैं तो इस फंक्शन की वैल्यू क्या होती है, यानी कि मैं अगर इस रियल लाइन पे किसी लेफ्ट हैंड साइड पे किसी पॉइंट पे खड़ा हूं, और वहां से मैं अगर धीरे धीरे अगर 0 के तरफ अगर अप्रोच कर रहा हूं, तो इस फंक्शन की वैल्यू क्या होगी। अब जैसे जैसे मैं इस 0 को अप्रोच करूंगा, वैसे सपोज इस वैल्यू पे मेरी x की वैल्यू ये थी, तो जैसे जैसे मैं 0 को अप्रोच कर रहा हूं, वैसे ही ये वैल्यू पहले कम हो, तो इस प्रक्रिया को हम कहते हैं टेकिंग द लिमिट ऑफ अ फंक्शन। यानी कि हम यहाँ पे लिख सकते हैं कि लिमिट ऑफ x टेंडिंग टू 0 फ्रॉम द लेफ्ट हैंड साइड, उसको मैं 0 माइनस से रिप्रेजेंट कर रहा हूं, साइन ऑफ x इज इक्वल टू 0। उसी तरीके से मैं राइट हैंड साइड से भी अप्रोच कर सकता हूं। मैं अगर राइट हैंड साइड से किसी पॉइंट से शुरू करके अगर 0 तक अगर अप्रोच करता हूं, तो क्या होगा, सपोज यहाँ पे मेरी फंक्शन की वैल्यू ये थी, तो यहाँ से फिर पहले वो बढ़ेगी, बढ़ते 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 फिर कम होना चालू होगी, कम होते होते वापस से वो 0 पे आ जाएगी। यानी कि इसे मैं लिख सकता हूं लिमिट ऑफ x टेंडिंग टू 0 प्लस, यानी कि फ्रॉम द राइट हैंड साइड साइन ऑफ x इज ऑल्सो इक्वल टू 0। तो यहां पे हम देख रहे हैं कि जो साइन ऑफ x की वैल्यू है एट x इक्वल टू 0 इज 0, साइन ऑफ x की वैल्यू in the limit of x tending to 0 from the left side is 0, and the value of sin of x in the limit x tending to 0 from the right side is also 0। यानी कि यहाँ पे ये जो तीनों जो वैल्यूज हैं, दो हमारी लिमिटिंग वैल्यूज और एक वैल्यू एट दैट पर्टिकुलर पॉइंट, ये तीनों इक्वल हैं। जब ये तीनों इक्वल होते हैं तब हम कहते हैं कि द फंक्शन इज कंटिन्यूअस एट दैट पॉइंट। तो यहां पे हमारा लिमिट्स से हम कंटिन्यूटी के कॉन्सेप्ट पे जाते हैं, यानी कि जब हमारा कोई एक आर्बिट्ररी फंक्शन हम अगर लेते हैं f ऑफ x, तो अगर f ऑफ a, सो इफ f ऑफ a इज इक्वल टू लिमिट x गोइंग टू a माइनस f of x is equal to limit of x tending to a plus f of x, then we say that f of x is continuous at x is equal to a। तो यहाँ पे आप कहेंगे कि ये तो बहुत ही ट्रिवियल सा कॉन्सेप्ट है, इसमें एक सेपरेटली इसे एक नाम देने की क्या ज़रूरत है। नाम देने की ज़रूरत इसलिए है क्योंकि काफ़ी सारे जो फंक्शंस होते हैं वो कंटिन्यूअस नहीं होते हैं, लेकिन वो बहुत इंपॉर्टेंट होते हैं। एक सिंपल एग्जांपल जो कि इस कोर्स में आपको बहुत काम आने वाला है, जिसके बारे में हम बार बार हम देखेंगे उसके वेरियस फंक्शंस को, वो है रेक्टेंगुलर फंक्शन। सपोज मैं एक फंक्शन लूँ x एंड दिस इज लेट्स से u ऑफ x। तो u ऑफ x इज अ यूनिट स्टेप फंक्शन, जो कि व्हेन x इज नेगेटिव तो ये फंक्शन 0 होता है, और जब x पॉजिटिव होता है तो ये फंक्शन यूनिटी होता है। तो इस फंक्शन की हम अगर लिमिट निकालें एट x इक्वल टू 0, तो हम देख सकते हैं कि वो सेम नहीं आएगी, क्योंकि हम जब इसे लेफ्ट साइड से अप्रोच करते हैं तो ये फंक्शन की वैल्यू 0 होती है, और जब राइट साइड से अप्रोच करते हैं तो इस फंक्शन की वैल्यू यूनिटी होती है। यानी कि लिमिट ऑफ x टेंडिंग टू 0 माइनस u ऑफ x इज इक्वल टू 0, बट लिमिट ऑफ x टेंडिंग टू 0 प्लस u ऑफ x इज इक्वल टू 1। यानी कि इस फंक्शन की लिमिटिंग वैल्यूज लेफ्ट साइड से और राइट साइड से सेम नहीं होती है, यानी कि u ऑफ x इज नॉट कंटिन्यूअस। तो जैसा कि मैंने आपको बताया कि सिग्नल्स एंड सिस्टम्स कोर्स में रेक्टेंगुलर फंक्शन बहुत इंपॉर्टेंट होता है। तो रेक्टेंगुलर फंक्शन क्या होता है? तो जैसा कि हमने अभी देखा यूनिट स्टेप फंक्शन में, हमने कि यूनिट स्टेप फंक्शन जो होता है वो नेगेटिव वैल्यूज ऑफ x के लिए 0 होता है और पॉजिटिव वैल्यूज ऑफ x के लिए 1 होता है। उसी तरीके से जो रेक्टेंगुलर फंक्शन होता है वो कुछ इसी तरीके का होता है, लेकिन उसे हम r ऑफ x के माध्यम से डिनोट कर सकते हैं कि वो नेगेटिव x के लिए हमने उसको 0 माना, पॉजिटिव x के लिए 1 माना, लेकिन अप टू अ पर्टिकुलर पॉइंट, लेट्स से सम x0। सो 0 से लेके x0 तक वो फंक्शन 1 होगा और x0 के बाद में वो फंक्शन वापस से 0 हो जाएगा। तो जैसा कि हम देख सकते हैं कि हम अगर 0 लें और 0 से हम अगर लेफ्ट साइड से अप्रोच करें तो इस फंक्शन की वैल्यू 0 रहती है। अगर हम राइट साइड से अप्रोच करें तो इस फंक्शन की वैल्यू 1 हो जाती है, यानी कि वो 0 पे तो डिसकंटिन्यूअस है ही, जैसा कि हमारा यूनिट स्टेप फंक्शन था, लेकिन वो x0 पे भी डिसकंटिन्यूअस है, क्योंकि हम x0 को अगर लेफ्ट साइड से अप्रोच करें तो हमारे फंक्शन की वैल्यू 1 होगी, और अगर उसे हम अगर राइट साइड से अप्रोच करें तो उस फंक्शन की वैल्यू 0 होगी। सो हमारा जो यूनिट स्टेप फंक्शन है इसमें है 1 पॉइंट ऑफ discontinuity, और r of x में there are 2 points of discontinuity. अब ये जो हमारा लिमिट्स है, लिमिट्स जैसा हमने देखा एक कंटिन्यूटी के कॉन्सेप्ट को डिफाइन करने में ये बहुत मदद करता है, लेकिन इसके अलावा लिमिट्स का कॉन्सेप्ट काफ़ी सारे फंक्शंस को इवैल्यूएट करने में भी बहुत मदद करता है। फॉर एग्जांपल एक और फंक्शन जो आप कई बार इस कोर्स में देखेंगे वो है f of x इज इक्वल टू साइन ऑफ x बाई एक्स। अब ये जो फंक्शन है ये x इक्वल टू 0 को छोड़ के आप कोई भी अगर इसमें x सब्स्टिट्यूट करें तो आप इस फंक्शन को बड़े आसानी से कैलकुलेट कर सकते हैं। लेकिन मैं अगर आपसे कहूं दैट फाइंड f of x at x इक्वल टू 0, तो आप इसे कैसे निकालेंगे? आप क्या करेंगे कि आप इस फंक्शन में x इक्वल टू 0 सब्स्टिट्यूट करेंगे, लेकिन उसे प्रॉब्लम क्या है कि साइन ऑफ 0 इज 0 एंड x एट 0 इज ऑल्सो 0, यानी कि ये जो हमारा फंक्शन है f ऑफ 0 ये हमारा आ जा रहा है 0/0 के फॉर्म में, तो इसे इवैल्यूएट करना डायरेक्टली बहुत ही मुश्किल है। तो यहाँ पे भी लिमिट्स का कॉन्सेप्ट बहुत काम आता है। तो इस तरीके के जो फंक्शन होते हैं जो एक पर्टिकुलर पॉइंट पे 0/0 या इन्फिनिटी यानी कि इस तरह के इनडिटर्मिनेट फॉर्म्स पे अगर आ जाते हैं तो उन्हें हम लिमिट्स को यूज करके इवैल्यूएट कर सकते हैं। कैसे करेंगे? हम अब लिखेंगे कि f ऑफ 0, हम अज्यूम करेंगे कि ये कंटिन्यूअस है और हम लिखेंगे कि दिस इज लिमिट ऑफ x टेंडिंग टू 0 f ऑफ x। ये हम कब लिख सकते हैं? जब हमारा लेफ्ट हैंड साइड लिमिट और राइट हैंड साइड लिमिट सेम हो, वरना हम ये नहीं लिख सकते हैं। और सो दिस इज इक्वल टू लिमिट ऑफ x टेंडिंग टू 0 साइन ऑफ x बाई x। अब जैसा कि हमने देखा कि डायरेक्ट सब्स्टिट्यूशन अगर हम करें तो ये 0/0 के फॉर्म में आ जाता है जो कि इनडिटर्मिनेट फॉर्म है। तो हम अब क्या कर सकते हैं कि हम साइन ऑफ x को पावर सीरीज के फॉर्म में रिप्रेजेंट कर सकते हैं। तो इसे हम लिखेंगे लिमिट ऑफ x टेंडिंग टू 0 1/x, और साइन x जो होता है वो है x माइनस एक्स क्यूब बाई 3 फैक्टोरियल प्लस x 5/5 फैक्टोरियल एंड सो ऑन। तो यहाँ पे अब हम देख सकते हैं कि जो हमारा ब्रैकेट के अंदर में हर टर्म में कम से कम एक बार x मौजूद है। तो हम x को हर टर्म से कैंसिल करके इसे हम लिख सकते हैं लिमिट ऑफ x टेंडिंग टू 0 1 माइनस एक्स स्क्वायर बाई 3 फैक्टोरियल प्लस x पावर 4/5 फैक्टोरियल एंड सो ऑन। अब यहाँ पे हम अगर x इक्वल टू 0 सब्स्टिट्यूट करें तो हमें कोई दिक्कत नहीं है, क्योंकि जो हमारा जो पहला टर्म है 1 वो 1 ही रहेगा क्योंकि वो कांस्टेंट है। सेकेंड टर्म जो है वो 0 हो जाएगा क्योंकि वहां पे x स्क्वायर है। थर्ड टर्म है वो भी 0 हो जाएगा क्योंकि वहां पे x पावर 4 है। वैसे ही बाकी जितने सारे टर्म्स हैं सभी में न्यूमरेटर में x का कोई पावर है लेकिन डिनोमिनेटर में एक कांस्टेंट है, यानी कि ये बाकी सारे जितने टर्म्स हैं वो सारे के सारे टर्म जो है वो 0 हो जाएंगे, यानी कि दिस विल बी इक्वल टू 1। तो यहाँ पे हमने देखा कि एक फंक्शन जो कि x इक्वल टू 0 पे इनडिटर्मिनेट फॉर्म का था, लेकिन लिमिट्स को यूज करके हमने उसकी वैल्यू x इक्वल टू 0 पे इवैल्यूएट कर ली। अब हम यहाँ पे ये भी चेक कर सकते हैं कि ये जो फंक्शन है उसकी लेफ्ट हैंड लिमिट और राइट हैंड लिमिट दोनों ही इक्वल है, क्योंकि इस यहां से हमने जो शुरू किया था और यहां तक हमने कहीं भी ये नहीं यूज किया कि वो लिमिट लेफ्ट हैंड साइड है या राइट हैंड साइड है। अब यहां पे आने के बाद में भले ही हमारी लिमिट लेफ्ट हैंड साइड हो या राइट हैंड साइड हो, हम जैसे ही x में जीरो सब्स्टिट्यूट करेंगे वैसे ही ये सारे टर्म्स जीरो हो जाएंगे, और ये कोई फर्क नहीं पड़ता कि आप जीरो को किस तरफ से अप्रोच कर रहे हैं। यानी कि इस फंक्शन की लिमिट लेफ्ट साइड से और राइट साइड से, दोनों ही साइड से, इज इक्वल टू 1। सो ये एक बहुत ही इंपॉर्टेंट रिजल्ट है जो कि हम इस कोर्स में आगे भी यूज करने वाले हैं। अब इस तरीके के जो फंक्शंस होते हैं जिनकी हमें लिमिट निकालनी होती है किसी वैल्यू पे, तो हम इसे पावर सीरीज के माध्यम से सॉल्व कर सकते हैं। लेकिन पावर सीरीज लिखना कई बार काफ़ी कम्बरसम हो जाता है, इसमें काफ़ी सारे टर्म्स होते हैं और कैंसिलेशन करते वक्त काफ़ी आप मिस्टेक्स भी कर सकते हैं। तो इससे एक आसान तरीका होता है जिसे कहते हैं एल हॉस्पिटल्स रूल। तो जो एल हॉस्पिटल्स रूल होता है उसके माध्यम से आप इस तरह के इनडिटर्मिनेट फॉर्म्स को बड़ी आसानी से कर सकते हैं। तो आइए देखते हैं कि ये एल हॉस्पिटल्स रूल क्या होता है। तो एल हॉस्पिटल्स रूल बेसिकली बताता है कि हमारे पास अगर कोई फंक्शन हो, सपोज लिमिट x टेंडिंग टू a सम f ऑफ x बाई g ऑफ x, और अगर f ऑफ a इज इक्वल टू 0 इज इक्वल टू g ऑफ a, तो हम क्या कर सकते हैं कि हम इस f ऑफ x का डेरिवेटिव निकाल सकते हैं। डेरिवेटिव क्या होता है? डेरिवेटिव इज रेट ऑफ चेंज ऑफ f ऑफ x, उसे हम डिनोट करते हैं f प्राइम के द्वारा। सो f प्राइम ऑफ x इज डेरिवेटिव ऑफ f of x, and what is f prime of a? f prime of a is derivative of f of x at x equal to a, और जो डेरिवेटिव होता है वो होता है रेट ऑफ चेंज, यानी कि f of a को हम ये भी कह सकते हैं, इट इज द रेट ऑफ चेंज ऑफ f of x at x equal to a। इसी तरीके से हम g प्राइम ऑफ a को भी डिफाइन कर सकते हैं। ये डेरिवेटिव कैसे कैलकुलेट करते हैं ये हम अगले मॉड्यूल में सीखेंगे, बट अभी मैं आपको सिर्फ बता दूं कि ये डेरिवेटिव का जो कॉन्सेप्ट है उसको यूज करके हम बिना पावर सीरीज लिखे इस तरीके के इनडिटर्मिनेट लिमिट्स को बड़ी आसानी से कैलकुलेट कर सकते हैं। तो एल हॉस्पिटल्स रूल क्या कहता है कि दिस लिमिट इज इक्वल टू f प्राइम ऑफ x बाई g प्राइम ऑफ x, यानी कि अगर हमारा f ऑफ x बाई g ऑफ x अगर इनडिटर्मिनेट फॉर्म में है तो उसका लिमिट निकालने के लिए आप दोनों फंक्शन का सेपरेटली डेरिवेटिव कैलकुलेट कीजिए और फिर आप उसका लिमिट निकालिए। अगर डेरिवेटिव लेने के बाद भी अगर ये इनडिटर्मिनेट फॉर्म में है तो आप इसका फिर से डेरिवेटिव निकाल सकते हैं, और तब तक आप डेरिवेटिव निकालिए जब तक कि ये उस इनडिटर्मिनेट फॉर्म से हट ना जाए। तो इसे कहते हैं एल हॉस्पिटल्स रूल। अगले मॉड्यूल में हम देखेंगे कि ये डेरिवेटिव होता क्या है और इसे कैलकुलेट कैसे।
Okay, now the thing is that so in this module we have understand that limit and continuity. So the application how to in the chemical the chemistry, that is application part of this is very very important. So if chemical kinetics, if you go thermodynamics, derivative part is there, limit continuity part application is there, so that is importance of this one. Okay, now we have to move another topic of that is matrices, right? So how the matrices is that is what is the formulas is there, row and column wise matrices is there. We have to understand the matrices while watching this video. Now we have to understand that how the matrices is working on
You should
this.
have listened to the spoken tutorials Getting Start Scilab by double clicking on as and press enter. Enter. It is easy to enter. The command returns all the elements and entry respectively inside the bracket. Also, any colon, comma, 2 colon 3.
Just a second.
where L was lower triangular and U was upper triangular. Fine. And there was a condition for that, in the sense that we needed that if I look at A, then first thing that we needed was that the A11 should be non-zero. Then what we had was that look at, if A was say this matrix, then the first entry was supposed to be non-zero, all right. At the next stage we wanted that this 2 cross 2 matrix, look at the determinant of that, that determinant should be non-zero. At the next stage we required that we had a 3 by 3 matrix here whose determinant should be non-zero. So somehow when I am trying to solve a system of equation, these determinants are coming into play, and we learned that in our school days how to compute the determinant till the level 3 cross 3. We will not worry about the determinant at this stage, but what we will see is that these determinants lead to what are called non-singular matrices. And this is what you saw, that the matrices which I was trying to multiply on the left, which I had obtained from the identity matrix, were invertible matrix. So, we would like to proceed with those directions and then come out with things. So, let us go back to the system of equations. So, if you go back to the system of equations, all right, then what are the operations we may do? So, generally what we do is, the first thing we do is that we multiply a equation by a non-zero number. That is the first thing that we do. An equation, say second equation by second equation minus c times, for some c's, the first equation. This is what we do, and we do similar work in the sense that we try to make some entry 0 in the first row, sorry, in the first column, then the second column, and so on, and proceed. Sometimes if we do not have a pivot at the right place, then we need to interchange two equations, all right. So, we need to interchange two equations, all right. Say ith and jth, all right. So, these are the three things that we do when we look at system of equations. What we saw is that all these equations, they get translated into the language of augmented matrix. So, then we have the notion of what is called augmented matrix, and we can do similar thing in the augmented matrix. So, what we do, we can multiply a row by a non-zero number. So, multiply a row by C which is not 0, I can do that, fine. Similarly, I can replace this equation. So, I can replace the second equation. So, if I have the augmented matrix as A and B, this is augmented matrix, then I need to replace the second equation, the second row. I want to replace it by second row minus C times the first row, all right. This is what we need to do. And similarly, if we want to interchange, then what happens is that if I look at this augmented matrix, the ith row here, so ith row is replaced by the jth row, all right, and the jth row is replaced by the ith row, all right. So, these are the equations. So, whatever we do for the system of equation, we need to do the similar thing for augmented matrix, fine. Now, the next thing is that how do I do it from the matrix perspective, all right. So, from the matrix product, how do I go about it? So, I will look at matrix product, all right. So, let us do it for only by 3 matrices. So, we start with the identity matrix I3, all right, and suppose I want to multiply the second row. So, second row I want to multiply by C, then the matrix that I need here is, I am not doing anything to the first row, I am not doing anything to the third row, I am only multiplying the second row by C. So, multiply the second row of identity by C. So, just write it here 0 C 0, all right. So, you are multiplying 0 1 0 by C, fine. So, that is the corresponding matrix that I need to look at when I look at matrix multiplication and multiplying from the left, or what is called row multiplication, all right. The second one is replacing here. So, what we do is, again here if I note here, there is no change in the first row, there is no change in the third row, and the second row is being replaced by second row, all right, second row minus C times the first row, all right. So, we write this matrix. So, minus T C corresponds to the first column here, fine. Now, here if I want to look at in place of I and j, suppose I want to interchange the second and third rows, all right. So, if I want to interchange the second and third row, I again go back to identity for me, all right. First row there is nothing, no change, second row is being replaced by the third row. So, this is the third row of identity, and the second row of identity is this, all right. So, these matrices that I get here, which relate to the system of equation, whatever we do for the system of equation, they are called elementary matrices. So, these matrices are called elementary matrices, all right. So, what are elementary matrices? It is the set of those matrices which can be obtained from the identity matrix by applying exactly one row transform here. Is that okay? So, again, so let us look at some examples so that better understanding. Example. So, I have identity with me, say I4, or let it be I3 itself for us, all right, and I want to look at what are called elementary matrices. So, there are 3 types of elementary matrices that we saw. So, let me write say E2 of 5. So E2 of 5 will be, second row is being multiplied by 5. So first row there is no change, second row is being multiplied by 5, and third row also remains the same. Fine. Then I have what is called E12 of say minus 5. All right. So it says that replace first equation of first row by minus 5 times by first row minus 5 times second row. So I am replacing the first row. So first row I have to take care of this, the first row is this, and then I am replacing by first row minus this. So minus 5 times the second row. So this is my thing is, there is no change in the second row, there is no change in the third row. All right. Then I have the last one, what is called say 1 3 of 1 3, which is interchange of, so interchange first and third row. So first row is being interchanged by the third row, there is no change in the second, and the first becomes the third one. All right. So let us try to understand this for an example A. So let me take the matrix A as 1 2 5 0 minus 1 0 and say minus 1 1 0. Suppose I have this matrix A. I want to look at what is E2 5 times A. So what we are doing is we are multiplying this to the first one. So first row is replaced by as it is. We are multiplying by 5 to the second row. So just multiply by 5, you get 0 minus 5 0, and the third row again remains the same. So we get this. All right. I can look at what is E12 of minus 5 times A. I would like you to see that this is nothing but the first row is being replaced, second and third remain the same. So the second remains the same, third remains the same. All right. First is this minus 5 times this. So since it is 5 times this, I just have to add it. So it is 1, 5 plus 2 is 7, I hope, and 5 here. Is that okay? So I am writing 1 2 5 and then minus 5 times 0 minus 1 0, which is 1, 5 plus 2 is 7, and 5, this is what we get. Then we have E13 of A will be equal to minus 1 1 0, 0 minus 1 0, 1 2 5. All right. So this is the way it is, but the important thing here is we are multiplying these elementary matrices on the left. Multiplication on the left. And why on the left? Because we are looking at system of equation. We are trying to solve the system of equation. So we are manipulating the equations, or we are manipulating the rows. All right. If I do it for example, if I want to look at what is A times E2 of 5, all right, then it is nothing but we are multiplying the second column. All right. So this becomes first column, there is no change. Second gets multiplied by 5, so it will become 10 minus 5 and 5. There is no change for the third one, it will remain 5 0 0. All right. So similarly, you have to look at the rest of it and compute the thing yourself. So these are called elementary matrices. What is important is for these matrices we also have an inverse. So let's look at the inverse of E2 5. So the inverse of this will be equal to E2 of 5 will be inverse of this is 1 0 0 0 1 upon 5 0 0 0 1. So why 1 by upon 5? Because we multiplied by 5, so we need to divide by 5. All right. What about the inverse here? E12 minus 5 inverse. Here the inverse has to be, here what we had done was we had added minus 5 times the second row to the first row. So I have to get it back. So get it back means I have to add 5 times. So I have to look at 1 5 0 0 1 0 0 0 1. So this is the inverse, and it turns out that for these matrices which are interchanged, the inverse is itself, there is no change as such. So this inverse will be equal to 0 0 1 0 1 0 1 0 0 itself, which you can see is same as E13, and is also equal to E13 transpose. Well, this is important that you get transpose here. So the inverse is same as transpose. That's very, very important here. Fine. So what we are seeing is that the notion of invertibility is basically saying that I have a matrix A, I multiply by a matrix and I get a result. Fine. So I have a matrix A, I multiply by some matrix P and get a Q. All right. Now I need to find inverse in such a way that P inverse by multiplied to PA, which is same as P inverse of Q, I should get back identity, I should get back A. So in the sense that this P inverse P should behave as identity. Is that okay? So these are the ideas that all these elementary matrices are invertible matrices, and they are the ones which we had used in the Gauss elimination method or to get the LU decomposition. All right. So we will proceed on this further in the next class. That's all for now. Thank you.
Okay, this is that is the matrix details. Now we'll move to the that is your probability, right? So we'll understand what is the probability.
Cases to E divided by total number of cases. Experiment or trial results in n exhaustive, mutually exclusive and equally likely outcomes, out of which m are favorable to the occurrence of an event E. Then the probability of occurrence of E is given by P of E equal to number of favorable cases to E divided by total number of cases, that is equal to m divided by n. Consider the random experiment of tossing of a die with numbers 1 to 6 written on its 6 faces. The sample space is S equal to the set containing points 1, 2, 3, 4, 5 and 6. Assume that the occurrences of all the 6 faces are equally likely. Consider the event A containing points 2, 3 and 5. Four are ace cards. Assumption that all possible outcomes are equally likely, but in many number 2 a red queen, number 3 a black card or a queen. Solution: let A be the event of getting a king card, B be the event of getting a red queen, C be the event of getting a black card and D be the event of getting a queen card. The content of a pack of 52 cards is 4 sets of 13 cards each, named as heart, diamond, spade and club. Among these, spade and club cards are black in color and heart and diamond cards are red. Each set of 13 cards consists of a king, a queen, an ace card and cards with numbers 2, 3, 4, etc. up to 10 written on them. Hence, in a pack of cards, there are 26 black cards, 26 red cards, 2 black kings, 2 red kings, 2 black queens, 2 red queens, 4 ace cards, etc. The problems are solving under the is having 52 equally likely possible outcomes. Number 1, the pack contains 4 kings, that is 4 out of 52 cards is represented as C union D. By addition theorem, P of C union D equal to P of C plus P of D minus P of C intersection D. Pack of cards contains 26 black cards. Hence, P of C equal to 26 divided by 52. Pack of card contains 4 queens. Hence, P of D equal to 4 divided by 52. Out of 52 cards, 2 cards are black queen cards. Hence, P of C intersection D equal to 2 divided by 52. Now, P of C union D equal to 26 divided by 52 plus 4 divided by 52 minus 2 divided by 52, that is equal to 28 divided by 52. Problem number 2. 2 unbiased dice are thrown. What is the probability of getting sum of the numbers shown is less than 5? Solution. When 2 unbiased dice are thrown, we can expect any of 36 equally likely possible outcomes. The sample space is S containing the points 1 1, 1 2, 1 3, etc., 4 5, etc. The last one is 6 6. Let A be the event of the sum of the numbers shown is less than 5. Out of the 36 outcomes, the following 6 outcomes are favorable to the event A. They are 1 1, 1 2, 1 3, 2 1, 2 2 and 3 1. Hence, probability of A, P of A equal to 6 divided by 36, that is equal to 1 divided by 6. Problem number 3. A box contains 5 red balls, 6 white balls and 3 blue balls. 2 balls are randomly chosen from the box. Find the probabilities of number 1, the balls are red. Number 2, the balls are 1 white and 1 red. Number 3, the balls are blue. Solution. The number of ways of choosing R objects from n distinguishable objects is n factorial divided by R factorial into n minus R factorial, that is equal to NCR. Hence, the number of ways of choosing 2 balls from the box of 14 balls is 14C2. The balls are randomly chosen. So, the 14C2 possibilities are equally likely. Number 1, to get 2 red balls from the box, the selection should be from the 5 red balls contained in the box. For this, there are 5 C2 different ways. Therefore, out of 14 C2 equally likely ways for choosing 2 balls from the box, the 5 C2 ways are favorable for the event of getting red balls. Hence, probability of the balls are red equal to 5 C2 divided by 14 C2, that is equal to 10 divided by 91. Number 2, to get 1 white and 1 red balls, 1 ball should be selected from the given 6 white balls and the other ball from the 5 red balls. Total ways for selecting 1 white ball is 6C1 and that of red ball is 5C1. If first job can be performed in n1 ways, second job in n2 ways, etc., the rth job in nr ways, then the entire R jobs can be performed simultaneously in n1 into n2 into etc. into nr ways. Now, the job of selecting 1 white and 1 red ball can be performed in 6C1 into 5C1 ways out of 14 C2 ways of selecting 2 balls from the box. So, probability of the balls are red and white equal to 6C1 into 5C1 divided by 14C2, that is equal to 30 divided by 91. As explained in earlier cases, the number of ways for getting 2 blue balls from the box with 3 blue balls is 3C2. Since the total number of ways for getting 2 balls from the box is 14C2, the required probability is 3C2 divided by 14C2, that is equal to 3 divided by 91. Problem 4. What is the probability that two persons in a room having same date of birth? Solution. The birth date of each one of these persons may be any of the 365 days in a year. We are ignoring the possibility of someone having date of birth on 29th February. Hence, there are a total of 365 into 365, that is equal to 365 square equally likely possible outcomes for the date of births of two persons. Probability of the two persons having the same date of birth equal to 1 minus probability of the two persons having different date of births. Let the first person is having his birth date on any one of the 365 days. For the occurrence of date of births on different days for these two persons, the date of birth of the second person should be any of the remaining 364 days. Hence, for the event of the two persons having different date of births, there are 365 into 364 possibilities out of 365 square ways of the total possible date of births. This gives probability of the two persons having different date of births equal to 365 into 364 divided by 365 the whole square, that is equal to 364 divided by 365. Thus, probability of two persons in a room having same date of birth equal to 1 minus 364 divided by 365, that is equal to 1 divided by 365. Conditional probability. The probability of an event A given that an event B of the same sample space has happened is called the conditional probability of A given B and is denoted by. Consider the random experiment of tossing an unbiased die. Let the event A containing the points 1, 3 and B containing the points 1, 3, 5. Then P of A given B is the probability of the outcomes 1 or 3 under the information that the experiment has resulted in an odd number, because B, the event containing the points 1, 3, 5 is an event of odd numbers in a die tossing experiment. Since the sample space of the experiment S containing the points 1, 2, 3, 4, 5 and 6, by the classical definition, the unconditional probabilities of A and B are probability of A equal to 2 divided by 6 and probability of B equal to 3 divided by 6. But when we are considering the conditional probability P of A given B, we are given the experiment was resulted in B. Now, it needs only to find how many cases of B are favorable to the event A. Here B contains 3 cases, out of which the 2 cases, that is 1 and 3, are favorable to A. Hence, the probability of the occurrence of A through B is 2 divided by 3, that is P of A given B equal to 2 divided by 3. In other words, the conditional probability P of A given B is the probability of A when the sample space of the experiment is reduced to the event B. Mathematically, P of A given B is defined as P of A given B equal to P of A intersection B divided by P of B, provided P of B not equal to 0, or P of B given A equal to P of A intersection B divided by P of A, provided P of A not equal to 0. From the above definition, it follows that P of A intersection B equal to P of A into P of B given A, where P of A not equal to 0 and P of A intersection B equal to P of B into P of A given B, where P of B not equal to 0. The above equations are known as the multiplication theorem for two events A and B. Independence of events. If the information that the event A has happened makes no change in the probability of the happening of the event B, we say that A and B are two independent events. That is, if P of B given A equal to P of B itself, we say that A and B are independent events. We have P of A intersection B equal to P of A into P of B given A, provided P of A not equal to 0. Then if A and B are independent events, we get P of A intersection B equal to P of A into P of B, provided P of A not equal to 0. Also we have P of A intersection B equal to P of B into P of A given B, provided P of B not equal to 0. Since for two independent events A and B, P of A given B equal to P of A, we get P of A intersection B equal to P of A into P of B, provided P of B not equal to 0. In short, two events A and B are said to be independent if probability of A intersection B equal to probability of A into probability of B, provided probability of A not equal to 0 and probability of B not equal to 0. Note: two disjoint or mutually exclusive events cannot be independent. Justification: take two disjoint events A and B. The events A and B are independent if P of A intersection B equal to P of A into P of B, where P of A not equal to 0 and P of B not equal to 0. Since it is given A and B are disjoint, P of A intersection B equal to 0. For them to be independent, 0 equal to P of A into P of B, where P of A not equal to 0 and P of B not equal to 0. But this cannot happen. Hence, two disjoint or mutually exclusive events cannot be independent. Problems. Problem number 1. Two unbiased dice are thrown. Let A denote the event that the sum of the numbers shown on the faces is odd, and B denote the event that at least one die shows the face with the number 1. Number 1. Describe the complete sample space. Number 2. Find probabilities of the events A complement intersection B complement, A intersection B complement, A given B, and A complement given B complement. Solution. The sample space contains 36 possibilities like 1 1, 1 2, 1 3, 1 4, etc. The last 6 6 as the set S. Since the given dice are unbiased, the possibilities are equally likely and each is with probability 1 by 36. Number 2. Here are the 18 points favorable to the event A, that is A equal to the set containing the points 1 2, 1 4, 1 6, 2 1, 2 3, 2 5, etc. The last is 6 5. Hence, P of A equal to 18 divided by 36. Out of the 36 cases, the 11 cases listed in B contains at least 1 1, where B is the event containing the points 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 2 1, 3 1, 4 1, 5 1 and 6 1. Hence, P of B equal to 11 divided by 36. Now, by De Morgan's law, P of A complement intersection B complement equal to P of A union B the whole complement, that is equal to 1 minus P of A union B, where A union B is the event containing the points 1 1, 1 2, 1 3, 1 4, etc. The last is 6 5. This contains 23 elements out of 36 equally likely possibilities. Then P of A union B equal to 23 divided by 36. This gives P of A complement intersection B complement equal to 1 minus 23 divided by 36, that is equal to 13 divided by 36. A intersection B complement equal to the event containing the points 2 3, 2 5, 3 2, 3 4, 3 6, 4 3, 4 5, 5 2, 5 4, 5 6, 6 3 and 6 5. Since A intersection B complement contains 12 elements, probability of A intersection B complement, that is P of A intersection B complement, equal to 12 divided by 36. P of A given B equal to P of A intersection B divided by P of B by definition. A intersection B is the event containing the points 1 2, 1 4, 1 6, 2 1, 4 1 and 6 1. A intersection B contains 6 elements. Therefore, P of A intersection B equal to 6 divided by 36. Hence, probability of A given B equal to P of A intersection B divided by P of B, that is equal to 6 by 36 divided by 11 by 36, that is equal to 6 by 11. Probability of A complement given B complement equal to probability of A complement intersection B complement divided by probability of B complement. We have P of A complement intersection B complement equal to 13 divided by 36, and P of B complement equal to 1 minus P of B, that is equal to 1 minus 11 divided by 36, that is equal to 25 divided by 36. This implies probability of A complement given B complement equal to P of A complement intersection B complement divided by P of B complement, that is equal to 13 by 36 divided by 25 by 36, that is equal to 13 divided by 25. Problem 2. A box of 10 items, 2 are defective. Items are randomly selected from the box one by one and
Mr. Sahu,
examined.
just unmute.
What is the probability that the 6th item selected is
Mr.
the
Sahu, just
last
mute your mic.
defective?
Prasant Sahu.
For the occurrence of the event, the 6th item is the last defective. The first 5 selections should contain one of the 2 defectives, and the 6th selection should be the second defective. Let A be
Mr.
the event
Prasant
of
Sahu,
getting
please
one
mute your mic.
defective from the first 5 selections, and B be the event of getting the last, that is second defective in the 6th selection. The required probability is P of A intersection B. We have P of A intersection B equal to P of A into P of B given A. Here, the first 5 items can be selected in equally likely ways. Out of these 5 items, to get 4 good and 1 defective, the 4 good items are selected from the 8 good items, and 1 defective is to be collected from the available 2 defectives. This can be performed in 8C4 into 2C1 ways. Hence, P of A equal to 8C4 into 2C1 divided by 10C5. If A has already happened, then the box contains 5 items, out of which 1 is defective. Hence, the probability of the occurrence of B under the condition that the event A already happened is the probability of selecting the last defective item from the box of the remaining 5 items. This gives probability of B given A equal to 1 divided by 5. Thus, probability of A intersection B equal to 8C4 into 2C1 divided by 10C5 into 1 by 5, that is equal to 1 divided by 9. Problem number 3. A and B are 2 independent events in the sample space S. Show that number 1, A complement and B, number 2, A complement and B complement are also independent pairs. Solution. Given A and B are independent events, this gives P of A intersection B equal to P of A into P of B, where P of A not equal to 0 and P of B not equal to 0. Since P of A not equal to 0 and P of B not equal to 0, P of A complement and P of B complement are also non-zeros. Number 1, here to show P of A complement intersection B equal to P of A complement into P of B. We have P of A complement intersection B equal to P of B minus P of A intersection B. P of A intersection B equal to P of A into P of B gives P of A complement intersection B equal to P of B minus P of A into P of B, that is equal to P of B into 1 minus P of A. This gives P of A complement intersection B equal to P of B into P of A complement. Hence, by definition, A complement and B are independent. Number 2. Consider P of A complement intersection B complement. By De Morgan's law, P of A complement intersection B complement equal to P of A union B the whole complement. This implies P of A complement intersection B complement equal to 1 minus P of A union B, that is equal to 1 minus of P of A plus P of B minus P of A intersection B, that is equal to 1 minus P of A minus P of B plus P of A into P of B, because A and B are independent events. Therefore, P of A complement intersection B complement equal to 1 minus P of A minus P of B into 1 minus P of A. This gives probability of A complement intersection B complement equal to 1 minus probability of A into 1 minus probability of B, that is equal to probability of A complement into probability of B complement, that is P of A complement into P of B complement. This implies A complement and B complement are independent.
Hello friends, welcome to the lecture. In today's lecture we will discuss some basic concept which is very useful in further course further lectures. So let us start. Differential equations are used to express many general laws of nature and have many applications in physical, biological, social, economical and other dynamical systems. In particular, the origin of differential equation may be considered as the effort of Newton useful information about the system if the equation were formed incorporating the various important factors of the system. So here if we consider let y equal to f to be a given function of independent variable t, then the change in y with respect to t can be represented as the derivative dy by dt. So in many real world process, the variable representing the important factor of the process and their rate of change are related to each other in terms of some basic principle of the process, which most of the times the representation of these relations in terms of mathematical forms turns out to be a differential equation, and in this way we can explain the technology. So let us start with the definition, proper definition along with some examples. So as the name indicate, a differential equation is a relation between independent variables, dependent variables and its first or higher order derivatives. So for example, if independent variable is t, dependent variable is y, it means that y is a function of t, and we can consider the first or higher derivative, it means that y dash t, y double dash t and so on. So any relation which relate t, y, y dash t, y double dash t and so on is considered to be a differential equation. Now depending on the number of independent variable, we may classify the differential equation in two parts, ordinary differential equation and partial differential equation. So in ordinary differential equation, there is only one independent variable. So let ft define a function of t on an interval I. Here I is open interval a to b, and by an ordinary differential equation we define an equation involving t, ft and its one or more higher derivatives. So, here are some example of ordinary differential equation. If you look at this first one is dy by dt equal to alpha y. Here alpha is any real constant which is a positive, and d2y by dt square as g, this is second example, and third example is dy by dt equal to 3y square sin t plus y. And fourth example of differential equation is m d2y by dt square equal to mg minus alpha dy by dt. If you look at the first example, here y is the dependent variable and t is the independent variable, and dy by dt is the first derivative of y with respect to t, and it is related to the variable y, dependent variable y, by this relation dy by dt equal to alpha y. This is a very commonly used equation in population dynamics, and it says that if the population say grows with the rate of alpha, then the population at any given time t can be obtained with the help of this differential equation. And if you look at the second equation d2y by dt square equal to g, basically this is what when you consider a particle say falling from a particular point, then this will represent the equation governing the motion of that particle, and it is given as d2y by dt square equal to g. Here this g represent the gravitational force, and this is third one is dy by dt equal to 3y square sin t plus y. Here this represent a particular say motion of some particle, and in 4 if you look at m d2y by dt square equal to mg minus alpha dy by dt, and if you look at this is similar to equation number 2. In fact, in equation number 2 we have ignored that there is any kind of friction due to air on this particle. So, here we are assuming that this particle is moving under only the influence of gravitational force, and there is no other say restriction on that particle is put. Now, but if we assume that this air, if this air put some kind of force upward, then we can modify the equation number 2 in this way. Here this alpha dy by dt represent the friction due to air. So, here this second can be modified in this way. Here we can write m d2y by dt square equal to mg minus alpha dy by dt. Here alpha represent the constant which says that the restriction or the force due to air is proportional to the velocity of the particle. So, if we assume alpha is 0, then this fourth equation is nothing but the second equation. So, these are some example of ordinary differential equation which we most of the time we came across to solving these equations. So, once we have the definition and the example of differential equation, let us discuss more basic thing about the differential equation. So, first thing is the order of a differential equation. So, the order of a differential equation is the order of the highest order derivative present in the equation. For example, if you look at here in first equation, the order of the highest order derivative is 1. Here we have only one derivative, and that is dy by dt equal to alpha y. So, here we have only one derivative and the order is 1. So, equation 1 is the differential equation of order 1. If you look at the second equation d2y by dt square equal to g. So, here we have only one derivative and that is of highest order. So, here the order of this differential equation 2 is 2, this 2. And similarly, the equation number 3 is a differential equation of order 1, and in 4 we have two derivative, two terms of derivative exist. First one is dy by dt and another one is d2y by dt square. But if you look at this is first order and this is the second order, so highest order is 2. So, we can say that this differential equation is of second order. And as we have pointed out, this equation 1 represent a very basic population model where a population is growing with the rate of alpha. And equation 2 represent an equation of a particle of mass m falling freely under gravity, while equation 4 may represent the same model, but now with the presence of air which exert an opposite force proportional to the velocity of the particle, that we have already seen. Now moving on next. So now we define what is partial differential equation. We have seen that the number of independent variable simply classify the differential equation into two part. One is ordinary differential equation and another one is partial differential equation. In ordinary differential equation we have seen that independent variable is only one. So there is only one independent variable and we are considering all the functions of that independent variable. So but in partial differential equation we may have, so in partial differential equation there is more than one independent variable, and so the derivative of dependent variable with respect to these independent variables are partial derivative rather than the ordinary derivative. So here, since number of independent variables are more, so if we consider any function of these independent variables, then if you consider the derivatives, then it is coming out to be partial derivative rather than the ordinary derivative. So that is why we call the equation which involve the function independent variables and the derivative of function with respect to these independent variable as partial differential equation rather than ordinary differential equation. So let us consider this example. This let utxy be a function of time t. This is a time variable and two rectangular coordinates of a point in a space x and y. So here x and y are space variable and t is a time variable. So here let consider u is a function of t, x and y, where t is a time variable and x and y are space variable. So let utxy be a function of time t, let utxy be a function of time t and the two rectangular coordinates of a point in a space x and y. Then consider the following three equation. First equation is dou 2u by dou x square plus dou 2u by dou y square equal to 0. So this is the relation where unknown function u is a function of x and y, and there is no partial derivative of u present in terms of t, and so it is a partial differential equation. It is an example of a partial differential equation. Now consider the second example where all these partial derivative present. So here this is k times dou 2u by dou x square plus dou 2u by dou y square equal to dou u by dou t. And third one is k times dou 2u by dou x square plus dou 2u by dou y square equal to dou 2u by dou t square. In these last two problems, this k is a constant, and depending on this problem, this k may have some values, and these are very famous examples of partial differential equation. So the above three equations are classical problems in partial differential equation and are widely used in application. So equation 1, 2, 3, these equations 1, 2, 3 given in 1, 2, 3 are classical in nature and widely used in problems of fluid dynamics, theoretical physics and many other related fields. And these equations are known as, the first equation is known as Laplace equation, the second one is heat equation, and third one is wave equation. So this is given here, Laplace equation, two-dimensional heat equation, space variables are 2. So this dimension is depending on the space dimension. So here we have two space coordinates x and y, so it is two-dimension heat equation. Similarly, this is two-dimension wave equation. Now coming back to differential equation. So what we try to do here, first we discuss the ordinary differential equation, we discuss all basic concept, existing uniqueness and related problems in ordinary differential equation, and then we will start with partial differential equation also. So first let us start with ordinary differential equation. So an ordinary differential equation of nth order is defined as follows. Here f is some function, smooth function, and it is a function of t y and yn. Here t is an independent variable, as we have already pointed out that ordinary differential equation contains only one independent variable. So here y is a function of this independent variable t. So f is a relation between t, y and yn. Here yn represent the nth derivative of y with respect to t. So here we can say that here yi, where I is from 1 to n, represent the ith derivative of the unknown function y, and here f is defined in some subset of R n plus 2 and provide a relation between the n plus 2 variables. What are n plus 2 variables? T, y, y dash, y double dash and yn. And but this is the general definition of ordinary differential equation of nth order. But because of the implicit nature of this function f, this may represent more than one differential equation, or we can say that it is it may represent the collection of differential equation rather than a single differential equation. Let us explore this possibility. Consider this differential equation y dash q minus 3t square y dash square plus 3y y dash equal to 0. If you look at, this is a relation between what? Here t is present, y dash is there, y is there, and yes. So here this is the relation between t, y and y dash. So it is a differential equation of order 1. But if you look at closely, then it gives not only one differential equation, but it is giving basically 3 differential equation at once. So it is given in the form 1, but it represents a combination of more than one ordinary differential equation. If you can solve this, let us right now this is given in a very nice form and we can solve it. So here we can solve it: y dash cube minus 3t square y dash square plus y dash equal to 0. So here if you look at, in all the terms your y dash is there, here y dash is there, here y dash is there, here y dash. So what we can do, we can take out this y dash out, and if you take y dash out, then first term is y dash square minus 3 square y dash plus 3y. Now here y dash, and if you look at in the bracket, we have a quadratic equation in terms of y dash. So we can solve using the theory of quadratic equation, and we can write this as y dash equal to 0 or y dash equal to 3t square plus minus under root 9t to power 4 minus 12y divided by 2. So if you look at this represent one differential equation, and this is the say basically 2 differential equation. So here we have this differential equation is not only one differential equation, but it is giving you the possibility of 3 differential equation. So in order to avoid this ambiguity, we assume that given ordinary differential equation is solvable in terms of the highest order derivative. So rather than considering the implicit nature, like here this is the implicit nature. So here we do not know that we are considering only one differential equation or a collection of differential equations. So to avoid this possibility, what we try to what we assume that this yn is solvable. We can solve this equation in terms of yn, and we can write our equation in this form: yn equal to g t y up to yn minus 1. Here g is some kind of function given in terms of n plus 1 variable, that is t y dash up to yn minus 1, and this form is known as normal form or canonical form. So now onward, whenever we try to discuss, we assume that our differential equation given in terms of normal form or canonical form. Actually this will avoid that the possibility of that multiple differential equation considered at one time. Okay. Now coming out to basic concepts, once we define what is a differential equation, we need to define what is a solution of differential equation. Similarly, we can define the solution of this differential equation in the following manner. So a function phi t is called a solution of 2 means this equation yn equal to g t y up to yn minus 1. If it satisfy the following condition. Here we need to consider that this T is belonging to at least some interval. Right now I am considering this as an open interval AB. So if it satisfies the following condition, first condition is that phi t is defined and it is n times differentiable on I, so that all these terms exist, y this n derivative of y exists and all the given derivative exist, right. And second is that this phi t satisfy the equation 2 for each t in I. So it means that it is not only all the derivative exists, but also satisfy this equation for all t in that particular interval. Then in this case we say that the function phi t is a solution of the differential equation. If any of these two fail, then we cannot say that phi t is a solution of equation 2. Now in this particular course, the aim of the study of the ordinary differential equation is to find the unknown function represented in an explicit form. So our first important aim is to find the solution. Solution means dependent variable in terms of t in explicit form. It means that your phi t is given in terms of t in elementary form, or we can say that in terms of elementary functions. Elementary functions are like for example polynomials, trigonometry functions, exponential function, all combinations of these elementary functions. And if you are not able to find out the solution in explicit form, then we try to find the solution in terms of implicit form, or we need to go further to study the behavior of a solution by available analytical methods. So suppose we are not able to find out the solution in explicit form, means your y is given in terms of some function of t. If we are not able to find out that, then we try to find out a relation between t and y, and in terms of like ft yt kind of thing, and it is known as implicit form. But suppose we are not able to find in these kind of explicit form, we try to find out the behavior of the solution by given analytical methods. We will discuss some of these analytical methods in due course of time. Now before proceeding further, we try to discuss the classification of the ordinary differential equation, or we say that before looking for a solution or any qualitative properties, we want to know the class or group in which the equation belongs to, right. So what are these class or groups? Let us define that. There are various ways available to classify the given ordinary differential equation, and some of the commonly used classification are listed as follows. First, based on the dependent variable. Okay. So what it means, that here dependent variables coming in linear manner or non-linear manner. And second classification is based on conditions. So if initial conditions are given, then we call our problem as initial value problem, or IVP denoted in a short form. Or if boundary conditions are given, then we say that our equation is boundary value problem. In short, we are writing BVP. What are these initial and boundary condition? We will come to know. So we say that we first classify depending on the number of independent variable, that is ordinary differential equation or partial differential equation. And then we try to define further classify in terms of dependent variable or conditions. So let us consider the first case, that classification depending on the dependent variable. So here we try to find out what is linear and non-linear differential equation. So let us consider the equation, this yn equal to gt y dash up to yn minus 1. So if the relation g is linear in its argument y to yn minus 1, so it means that look at the variable of g. Here it is variable is t, y and yn minus 1. These are the argument of this g. So t represent the independent variable. So we need not to check, we need not to bother about the that g is coming in terms of g is linear with respect to t or not. We need to consider the argument which are dependent variables. So, it means that if G is linear in terms of y to yn minus 1, then we call this equation 3 as linear ordinary differential equation. Otherwise, it is called a non-linear ordinary differential equation. For example, if you look at this first problem, it is y dash plus ky equal to 0. If you look at arguments of what, it is y dash and ky y. So, here y dash is coming linearly, y is also coming linearly. So, we can say that this equation is a linear differential equation. Here k is a real constant. Now, and if you look at this second equation, dy by dt equal to y square, if you look at here, y is not coming in a linear manner. So, we can call this differential equation dy by dt equal to y square. By the way, here I am writing that this is a y and y dash are coming in a linear manner, and here y is not coming in a linear manner. What do you mean by that? We are going to explain. Because here I can say easily that okay, this is a linear differential equation, and here since y is coming in terms of powers of y, so we say that it is a non-linear differential equation. But if you look at this equation y dash plus mod of y equal to 0, it looks that all these y and y dash is coming in a linear manner, but we really it is quite difficult to say whether it is linear or a non-linear ordinary differential equation. So, we need to devise a method by which we can check that okay, the first one is linear one, second one is non-linear one, and third one is whether linear or non-linear one. So, let us devise a method. So, here we consider the following equation. So, let us consider the following differential equation of order 2. We can we can do this process for any kind of differential equation of any order. So, let us for the time being, let us consider the differential equation of order 2. So, we define Ly as the following operator. Here Ly is equal to y double dash plus pty dash plus qty. It is kind of an operator which operate on y and give rise to this RT. So, it means that you put this y, then this will give you the value RT. So, it is an operator. So, this operator is defined like this: Ly equal to y double dash plus pty dash plus qty. Now, if this operator L is linear, we call the differential equation a linear differential equation, otherwise it is a non-linear differential equation. So, how to check that this operator is a linear operator? So, look at this here, the notation Ly suggests that the operator L operates on a function y to give this y double dash plus py dash plus qy as its value. So, it is a kind of an operator defined on the set of all functions where this y is coming, and it gives you another function of t. So, here Ly give rise to y double dash plus pty dash plus qty. So, we can consider that L is a operator from Vk to Vk, and here V is a vector space V defined on this scalar field K. So, let us say that an operator L from defined from Vk to Vk is said to be a linear operator on a vector space V defined on a scalar field K if it satisfies the following equality. So, what is this equality? That if L operating on alpha x plus beta y is equal to alpha times Lx plus beta times Ly, and this is true for all xy coming from this vector space V and all alpha beta coming from this scalar field K. So, if it is true for every xy in vector space V and every constant in K, then we say that this L is a linear operator, otherwise it is called as a non-linear operator. So, once we know how to define a linear operator, now with the help of
So
this,
now
let us
we have to understand that is
see what is
somewhat we got the idea about the linear
linear
differential
equation or
equations.
non-linear
So now we'll
differential.
understand that is matrix algebra. That's I am sharing the video matrix algebra. So go through that one.
unique solution. And there are multiple cases where the solution will not have unique solutions. One case is that the solution will not have any solution, the equation systems will not have any solutions, or we will call that to be a inconsistent system of equation. And there can be another case when infinite solutions exist for given equation system, and usually these cases arise when number of variables or number of independent variables is not equal to the number of equations given to us. And then we will look into different types of solvers. One is the direct solver and another is iterative solvers. Direct solvers, that as the name suggests, directly solves the matrix equation, gives us what is the solution in terms of for sparse linear systems. Its second edition was published within a matrix are called its rows, and the vertical says there are three matrices shown here, and entry of the matrix or can be an irrational number, can be any real number, can be complex number. Also there are cases where these entries are logical entries, or we can have Boolean matrices. Now if we look into each matrix, it's, as I said, it's a rectangular array of numbers, and we can see both vertical arrays which we call columns, and we will also see horizontal arrays which we call rows. Now rows and columns are also matrices, even a single number can also be thought of a matrix. Now as I said, entries of a matrix can be any type of numbers, it can be real, complex, integer, imaginary, irrational, and we may have Boolean matrices also. So a matrix is usually given as a rectangular array where the entries can be anything which is shown as a matrix, which has number of entries inside it as directed along rows and columns. So it has it has total 1, 2, 3, 4 n number of columns and 1, 2, 3, 4 m number of rows. So this, if we look into this matrix, there are total m rows, 1, 2, 3 m rows and 1, 2, 3 n columns, and inside this matrix any number can be identified by its position according to row and column. For example, this number goes to the third row, sorry, second row, this number goes to second row and 1, 2, 3 third column. So each entry inside the matrix will have a unique identification based on its row and column, and we can see this matrix has m rows and n columns, and the matrix A is said to have an order m into n, and is usually written when we need to show its order also A and in subscripts m into n, and each element in A is identified by its row and column index. So Aij is an element, small aij is an element of the matrix capital A, small aij is an element of the matrix capital A with ith row and jth column. Okay, this is how an element inside the matrix is defined, and the order of the matrix is also defined. Now one dimensional matrix is called a vector. That means a row is also a vector. If m is equal to 1, the row will become a vector, for like 1, 2, 3, 4 arranged in one horizontal array is a vector, and if n is equal to 1, that is also a vertical array which is called a column vector. So there are two types of vectors, usually row vectors and column vector, and a matrix which has only one entry, 1 into 1, that is also a rectangular arrangement if we see, and that is called a scalar. Any vector can be represented by a matrix of real numbers. That means when we talk about a vector, for example, say we talk about 2I plus 5j, which is a vector. So, in x direction there is 2 units, in y direction there are 5 units, and we can write it as 2 and 5, these two numbers. Similarly, a three dimensional vector can be written as a column of row size 3, or the column with or column matrix with order 3 into 1. There are 3 rows and 1 column. So, instead of 2D and 3D, because we are dealing with a very large system of equations in several times, we think of higher dimensional matrices, and higher dimensional space is not a physical space, but we imagine the physical space to have more and more dimensions after the third dimension, which of course you cannot easily visualize, but we can think of it. So, for example, I have x, y, z and I think of another coordinate zeta, that gives me a 4 dimensional space. Similarly, a higher dimensional vector can also be represented as a column matrix. It will have 1, 2, 3, 4, 5, 6, 6 entries. So, this is a in a 6 dimensional space, a vector in a 6 dimensional space, and several times we have to work with higher dimensional spaces in matrix algebra. So, we start looking into some of the important matrices. Basically, we look into the definitions of these things. So, when the notation is used, we will figure out that actually this type of matrix has been discussed. So, one is a 0 matrix, a matrix which has all elements 0, and it can be matrix of any order, like for example, if we write by O 2 into 2, that will be a 0 matrix which has 0, 0, 0, 0, which is of 2 into 2. Similarly, if we write O 1 into 4, that will be this 1 means it has 1 row. So, it is a row vector with 4 columns. So, again there are 4 zeros. In any space, a vector, a 0 vector or a 0 especially a 0 vector in any space will denote the origin, where all the coordinates are 0. So, next is not a 0 vector, 0 matrix, rather a matrix where most of the elements are 0, sorry, most of the elements are not non-zero, where there is I am sorry, there is a mistake here. So, we should make it a vector where most of the elements are 0. A sparse matrix is a matrix in which most of the elements are 0. For example, if we think of a matrix, say 1, 2, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 2, like this. Like there are 15 entries 3 into 5. So, this matrix has an order which is 3 into 5. Among these 15 entries, only 5 are non-zero. So, these are called sparse matrix, where most of the elements are 0, and this type of matrices are often arise while we are solving physical systems. So, physical systems analysis often give sparse matrices, and we will see sparse matrices in as a class of matrix coming from problems in computational mechanics, especially as example, and there are specific matrix solving algorithms which are designed for sparse matrices because of their huge applicability. And as this is a little qualitative definition that most of the elements are 0. So, quantitative definition also comes on sparsity, that is the total number of non-zero elements divided by total number of elements. For example, in this particular application, total number of elements is 5 into 3 15 and non-zero numbers are 5. So, sparsity will be 5 by 15. Sparsity should be very low in order to have a sparse matrix. And if the non-zero numbers are configured to a diagonal band, then we call it to be a banded matrix. For example, if we have a matrix like this 1 2 1 2 0 0 0 1 2 0 0 0 1 2 0 0 0 1. So, all the non-zero numbers are distributed along a band near the diagonal, and this is called a banded matrix. There is a dense matrix where opposite to sparse matrix most of the elements are 0 and density will be 1 minus sparsity. So, number of zero values divided by total number of 0 elements divided by total number of elements. A square matrix is where number of rows is equal to number of columns, and which is in a square matrix the entries with same row and column index are called the diagonal entries. So, if we see an example, for example, in this matrix 1 2 3 4, the entries with I is equal to 1 and j is equal to 1, I is equal to 2 and j is equal to 2 are the diagonal entries. Similarly, if we take a 3 into 3 matrix, say let 4 5 6 7 8 9 10 11 12, the diagonal entries are identified as 4 8 12. So, which has same row and column index, and if a square matrix has all the off diagonal non diagonal entries 0, we call it to be the diagonal matrix. So, only the diagonal values are non-zero or may be non-zero, there can be some zeros also, but all the off diagonal values should be 0. So, a matrix like this 1 0 0 0 1 0 0 0 1 is a diagonal matrix, or a matrix like 5 0 0 root 3 is also a diagonal matrix, where only the diagonals are non-zero. So, a question comes whether a diagonal matrix is a sparse matrix or not, and of course, because most of the elements are 0 here, only very few elements are non-zero, and if we see the definition of the sparse matrix, that if we see the definition of the sparse matrix, where most of the elements are 0. So, if we have anything greater than a 2 by 2 ordered matrix, we will have the diagonals only non-zero, off diagonals are much more than the diagonal terms, and therefore, it should be a sparse matrix. Rectangular matrices, so we are discussing only about square matrices. They are rectangular matrices, in which case, in cases they follow the definition that the terms with different row and column indexes are 0 are called matrices with rectangular diagonal form, and an example can be a rectangular matrix 1 0 0 0 2 0 0 0 3 and 0 0 0. So, this matrix has number of rows more than number of column. So, any row which is beyond than the maximum column ID should have all zeros for this form. Similarly, if we have a say 2 into 3 matrix 1 0 0 0 2 0, this is also of diagonal form, and any column which is more than maximum row number should have all 0 entries here. So, these are few of these definitions, we will see few more. we'll see some of the important more important matrices. One is a diagonal matrix must be a square matrix. If diagonal entries are 1, it is called an identity matrix, and identity matrices are generally denoted by I. For example, I 2 into 2 is 1 0 0 1, I 4 into 4 is equal to 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1. And now there is a restriction on what type of entries will these matrices have, and these will only have integers, because 1 is an integer in their diagonals. We cannot have complex matrices or imaginary entries in a identity matrix. There are some other definitions. Upper triangular matrix, let me clear this. Upper triangular matrix is a matrix for which any term which has a row index more than column index is 0, and it looks like a triangle, and it is also for a square matrix. So, if we have, for example, if we have a 3 by 3 matrix, one, 2, 3, this is first row and first row and column is 1 2 3. So, this is non-zero. This is second row, the column number is 1. So, this is 0, maybe 2 4, and this is 0 0 5. This is a what is called an upper triangular matrix. It can be something like this also, 1 2 3 4. Again, this is first row. So, first column onwards everything is non-zero, but second row first column is 0, 1 2 3 0 0 1 2 0 0 1, maybe root of 3. It can have any entry in that sense, and the lower triangular matrix is the opposite one. So, we can see that the matrix actually the numbers given in the matrix, sorry, this is 0, I am sorry, this is also 0. The non-zero numbers given in the matrix forms a triangular shape, and a lower triangular matrix is just the opposite. It has, where the column index is more than row index, it will be 0. So, 1 0 0 2 3 0 0 4. Interestingly, it is mandatory that these terms, the terms with column ID greater than row ID, or in case of lower triangular matrix like these terms, or in case of upper triangular matrix row ID greater than column ID has to be 0, but any of the other terms or many of the other terms can also be 0. A sparse matrix can have lower triangular and upper triangular form in that sense. We go to upper triangular and lower triangular form of rectangular matrices, a matrix which is not
Okay, so now the thing is that we have understand some of the, that is matrix, and that is algebra for matrix. So mathematics is an important part of the chemistry. So on the basis of that, you have to calculate, you have to apply all the things. So thank you very much for today.